The Philippine island of Batanes no longer COVID-19 free. The local government confirms a 29-year-old male who arrived in the province on September 22 tested positive for the virus. He is asymptomatic and now under isolation at a quarantine facility. The local government says the patient stayed at a quarantine facility in Santa Rosa, Laguna before traveling to Batanes.
World health officials this morning are reporting the first coronavirus death outside of China. A man from Wuhan, China, has died in the Philippines.
Cases in the Philippines will stand at around 2,000 until the end of the year. Professor Joma Rabahante of the
The COVID-19 pandemic had a devastating impact on the Philippines, affecting millions of lives and overwhelming healthcare systems. This experience highlighted how crucial it is to understand the dynamics of disease transmission. The creation and study of simulation models, like what we created, are not just tools for scientists and experts. They are essential for everyone to fully grasp how rapidly and destructively viruses can spread and why timely interventions matter. This presentation explains the Epidemic Spread Simulation Project, a simple but a powerful visual model that shows how a disease can spread among people in a closed space. It uses basic ideas from computational science to help users see and understand how diseases behave. The simulation lets users change settings like the transmission rate, distance moved, and the number of interactions. These changes help show how small differences in behavior or environment can lead to a very different results. The project highlights how useful computer models are for understanding things that are hard to see in real life. By following important ideas from human-computer interaction or HCI, such as making the simulation easy to understand, giving quick and clear feedback on what is happening, and designing controls that are simple to use, the simulation helps users learn to understand and stay interested. These design choices make sure people can focus on playing with the simulation and seeing how it works, instead of getting confused by complicated buttons or unclear information.
The main goal of the simulation is to help people learn and explore how a disease may spread. It gives user controls over three key settings. The first one is transmission rate, the chance that an infection happens when a sick person meets a healthy one. And the second one is distance travel, how far each person can move around. This can represent rules like lockdowns or how free people are to go places. And the third one is the number of contacts, how many people a sick person randomly meets per round, simulating crowded areas or person habits. By adjusting these settings, users can try out different situations and see how public health, decision, or social behavior may affect the spread of a disease. This simulation is for many kinds of users, such as person is students in public health, computer science, or science classes who wants to see how systems work. It helps them understand how disease spreads by watching it in action rather than just reading about it. They can also use the simulation for projects, assignments, or personal study. The second one is the teachers and instructors, who wants to show real-time models during lessons. These tools make abstract ideas more concrete and can spark discussions or activities. It also provides a visual way to explain cause and effect in science or health topics. And lastly is the health workers and researchers, who want a quick and simple way to explain or test ideas. They can use it to communicate the impact of policies like social distancing or high contact rates. It's also helpful as a lightweight tool for brainstorming or educational outreach. And for the user-centered design, UCD, perspective in development. Although direct user research such as interviews or surveys was not conducted, we approached the design and development process with a strong sense of empathy and simplicity. Informed by our own experience such as student and user to align the simulation with user needs, we focus on the person is the simplicity and clarity, avoiding unnecessary complexity in both interface and functionality to ensure the simulation remains accessibly and easy to understand. And the second one is the essential controls, including only the most important adjustable parameters: transmission rate, movement distance, number of contacts, to give meaningful interactivity without overwhelming user. And for the lastly is the intuitive interaction, designing controls and visual feedback so that users can quickly grasp how their change affect the simulation, fostering learning through exploration. This approach ensures the project stayed user focused by prioritizing clarity and usability, even without formal users involvement or testing.
So the first one will be the simulation modeling. So simulation modeling is when we use computers to mimic real-world systems. We build small versions of the system in code so we can see how they behave over time. So its implementation is, in the simulation, each person is a small object with properties like location and health status. So as the simulation runs step by step, it updates each person and shows how the infection spreads through the group. So this gives a visual and interactive way to study behavior over time. So the next one will be the random number generation. So random number generation allows us to introduce uncertainty into simulations. It's important because real-life situations are often unpredictable. So its implementation are the code uses to decide how people move, who a person meets, and whether someone gets infected. So these random decisions make the simulation feel more like lifelike because they add unpredictability just like in the real world. So the next one will be the probability systems. So a probability systems uses chance instead of fixed outcomes. So this means events happen because of likelihood and not certainty. So its implementation are when a sick person meets someone healthy, the simulation doesn't always make the healthy person sick. Instead, it uses a probability from the transmission rate slider to decide. This makes the spread more realistic, just like in the real life, where not every contact spreads disease. So the next one will be loops and control flow. So control flow determines how a program runs its steps. Loops let us repeat actions again and again, which is perfect for simulations. So its implementation or the simulation uses a loop created with that runs continuously. So each run of the loop updates the positions of people, check who gets infected, and redraws the screen. So this repeating cycle is what keeps the simulation running smoothly, like a video. So the next one will be a time-based simulation. So a time-based simulation updates step by step in small chunks of time, which helps us see how things change gradually. And its implementation are the program tracks time using timestamps. So it counts how many seconds pass and updates the animation at regular intervals. So this makes it easier to watch how infections grow over time. So rather than everything happening instantly, it also helps compare how fast or slow the disease spreads under different settings.
Why this matters in the real world? As we've seen with COVID-19, simulation like this help. First one is experts test what might happen if they change health rules. The second one is show how things like social distancing or mask wearing might work. And the lastly is teach people why even small actions matter in a pandemic. Even though this simulation is a simple, these same ideas are used in large-scale computer models that help government plan and make decisions. The first one is the JavaScript, used for the main logic, behavior, and calculations. And the second one is HTML5 canvas, used to draw the people and movement on the screen. And the third one is web controls, sliders, and buttons. Let users change values while the simulations runs. And lastly, browser rendering. Use requests animation frame to make sure animation are fast and smooth.
Now let me walk you through this piece of code which is responsible for generating our population in the simulation. We start by declaring an empty array called people. This will store all our simulated individuals as objects. Then we use a for loop that runs from 0 up to population size, which determines how many people we want in our simulation. Inside the loop, we're pushing a new object into the people array for each person. Each object represents a single person and contains 3 key properties: the x and y, which are random coordinates within the canvas area defined by width and height, and the third one, which is the state, which determines the health status of that individual. We use a simple condition. If the index I is 0, we assign the state as infected, meaning the very first person starts off infected. All the rest are initialized as susceptible, which means they are healthy but at risk of being infected. This setup lets us easily update and track each person's status in the simulation as it progresses. Now, let us take a look at how we simulate natural movement in the environment. Now, this snippet updates each person's position slightly each round. Here's how it works. Using the math_random function -0.5, it gives us a value between -0.5 and 0.5, which allows movement in any direction. Multiplying it by the travel radius and the movement factor controls how far and how fast the person moves. As a result, each person moves a small step in a random direction every frame, mimicking a realistic human motion like walking in a park or a public space. Now let's see how infection spreads from one person to another. Now this part of the code models disease transmission. So what's happening here is that we first check the distance between two people. If they're close enough, like less than the travel radius, they are considered in contact. Then we check if the other person is in a susceptible state, meaning they're still healthy. Lastly, we use a probability check. Using the math random function, less than transmission rate, it simulates the chance of infection using probability. We use the math.random function, which gives us a random number between 0 and 1. Then we compare it to the transmission rate, which is a value like 0.2 or 0.5, representing a 20% or 50% chance. If the random number is less than the transmission rate, then the infection happens. This mimics how infections occur based on the proximity and chance, just like in real-world virus spread scenario. Finally, we need to find a way to keep the simulation running over time. Now that is where this loop comes in. So it is a recursive loop driven by a request animation frame which schedules the next frame for smooth animation. It calculates delta, which is the time difference between frames, to ensure consistent timing regardless of frame rate. We then call update function to handle logic like movement and infection, and the draw function to display everything on screen. Now this loop keeps running continuously, allowing us to observe how the infection spreads over time.
So too much movement. So at first, people move too quickly, making it hard to follow. So a movement factor was added to slow things down. So no end condition. So the loop kept running even after all were infected. A check was added to stop the simulation once that happened. So user controls not syncing. So sliders and values weren't updating right away. So input event listeners were used to fix this. So performance drops. So the animation became slow with many people. So the code was optimized to reduce redraws and keep things fast. So what are the ideas for future versions? So add recovered or immune people. Next will be the include a delay for infection to show symptoms. Next will be the add zones or areas that people can move between. And lastly, simulate vaccination or immunity over time.
So this is the basic demonstration of the simulation that we made. So as we presented, it is entitled Epidemic Spread Simulation with the limited parameters that the users can play with. So it includes the number of encounters, the travel radius, and the transmission rate. So basically the number of encounters is how many the infected people will have an interaction within the day, and the travel radius is basically how far the infected will go based on its default location. And lastly, the transmission rate is basically how infectious the virus is. So by default, it will have 1, 1, and 0, which basically means that the virus is not actually, there's actually no virus because there's no transmission rate. So this red dot will not infect anyone in this kind of settings. However, if we try to play this, like increasing the transmission rate, let's say, let's increase this to 100 or to 1, basically an absolute, and then increase the travel radius by a little bit, and then the encounters by just a little bit, we should now observe that this red dot will start infecting other people. So in just a few seconds, from this default location, the epidemic or the virus actually now spread from all over the samples that we have. And by playing this, you can see that in just 6.6 seconds, all the objects or all the people that we have in the simulation are now infected. Now, again, the factors that affect all these decisions is based on the parameters that we have. So our transmission rate is very high, which means any contact will be done by the infected people will guaranteed a transmission. So just like so by reducing this, we should now see basically a reduced complete spread at time. So if we got 6.6 on a 100% transmission, we should have a longer, or it will probably more than 10 seconds to have a complete spread in this kind of parameter settings. So let's hit reset. So as you can see, comparing it to the initial simulation we have, this is much slower. So we did not change the encounters per day and the travel radius, but we changed the transmission rate, basically how infectious the virus is, or the chance that the virus will infect other people. So 30 seconds had already passed and still a complete spread is still not achieved. So in about 63 seconds or 64 seconds, we now achieve a complete spread. So it is basically our assumption, which is correct, that lowering the transmission rate will make the complete spread slower. So from the 100% transmission rate, which only took 6.6 seconds, it now took a 60 seconds, basically a 1 minute, to have a complete spread on basically a 0.5 or half of the transmission rate that we have earlier. So what if we do this same transmission rate, but we increase the number of encounters that we have per day? So let's say 30. So assuming that in this kind of situation, our predicted output should be, the complete spread would be much lower than 60 seconds, because the infected people will have a more encounters, so they will have to interact with other people, so that the chance of infecting them will be also much higher. So let's hit reset and let's check how long it will take for a complete spread. So as you can see, it took 48 seconds to have a complete spread on the parameter of 30 number of encounters, which is I think 20 points higher than the previous one that we made. So in this instance, you can see that we achieve our assumption or our predicted output that it will be much lower. So we could further lower this complete spread, basically a much faster spread, by increasing the travel radius. But I want to give a heads up that by increasing the travel radius, the movement of the objects that we have in this simulation will be much faster. This is because the computation for the travel radius, as we presented earlier, is that the higher it is, the faster the movement of the objects that we have. So you will see that basically in this demo, so I'll increase it from 5 to 12. So I'm gonna hit reset. So as you can see, it is much faster. So the movements of each objects here in this part of simulation is much faster compared to the earlier version that we made. And just like that, we have a much faster complete spread, just 8.1 seconds. So this shows that the amount of distance that a person travels really affects the complete spread of a virus. So this is the reason why um, social distancing and quarantine zone is actually created, so to make sure that those infected will not travel farther, will not travel, so to make sure that there's a reduced number of infections. So as you can see, by increasing the encounters of an infected people and its travel radius, it will also have a higher complete spread. So even if we lower this transmission rate, let's say 20, just 20 or 0.20, it will still have a very fast, a complete spread, even if it has a lower transmission rate, which is very similar to a COVID-19, which is basically it's not that little and has a lower transmission rate. However, if we travel, if a person, infected person has a wider or large travel radius and has a lot of interaction or encounters per day, then the spread of the virus is still guaranteed. So let's say that in this simulation. So as you can see here, even if the transmission rate is really low, the parameter of encounters per day and the travel radius makes this a complete spread much faster. If you remember the first one that we made, which is a 100% transmission rate but with limited or the default value would be basically 1 encounters per day and 1 travel radius and 100 transmission rate, it will still have a much lower, basically it will take much longer to have a complete spread. So let us see with that. So the transmission rate would be 100 and the travel radius would be 1 and encounters per day would be 1. So this shows that the virus is very lethal. So if a person has a contact with another infected one, then the spread of the virus is guaranteed. However, in these instances, we only have 1 travel radius and 1 encounters per day, and you will see that it will take so much lower. I'm sorry. So as you can see here, like I said, the travel radius affect the movement that we have in the simulation. So there's a little movement here because our travel radius is basically 1. So I already conducted this simulation, and based on my previous trial, basically I got up to 50 minutes, a complete spread. So it took me, it took the simulation 50 minutes to have a complete spread in this kind of parameter, which shows that the encounters per day and the travel radius is basically the one that shifts the our simulation. For the conclusion, this epidemic spread simulation is a great example of using simple computer models to explore real-life problems. It shows how small choices can lead to big changes and helps people understand the chain reaction in disease spread. Using basic tools like JavaScript and HTML5, the project brings together randomness, probability, time steps, and user interaction. It proves how computational science can turn ideas into real tools for learning and decision making. By using simulation like this, students and professionals can better understand how to solve complex problems in health, behavior, and planning. It is a step toward using computers not just for tasks, but for thinking and discovery. Furthermore, the desired results from tests created for the simulations were successfully achieved, with outcomes aligning with the expected behavior, validating the model's effectiveness and reinforcing its educational value.